Hello, in this example we're going to do a brief definition of continuity but then get into a nice example. So continuity has the following definition. A function f of x is continuous at some particular x value, a, at a number a, so this is the x value, if you satisfy the following three conditions. F of a is defined, so that's our first one. F of a is defined means that there is a y value that exists on this function. Number two, the limit as x approaches a of f of x exists. Okay, so it's not just f of a has to exist, meaning that there's a y value on this function, but the limit of f of x also has to exist. You'll see how all of these are needed to show continuity. And then the third, the limit as x approaches a of f of x has to equal f of a. Okay, so this is actually the y value. This is telling me it's telling me where I expect the y value to be as I approach a, and this is basically saying that what I expect the y value to be is actually the y value. So let's take a look at an example. So we have our function f of x right here. So let's go through the three conditions. F of a is defined. Well, on the graph, that would mean that there's an actual point that exists at a. So there's my y value right there. The limit of f of x exists, meaning that when you're following the graph, a limit existing means that when you're coming in from the left and right, it's approaching the same point. Okay, and then the third condition, when we're saying that the limit has to equal the y value, again, it's not enough to just say a y value exists. It's not enough to just say that the 2 points are going to the same spot. But the points, or the limit, telling me where I expect to be going is actually where the y value is. So notice that there's no breaks. Okay, you go right through that point. So another way of defining continuity in a very non-mathy way would be when you are tracing the function or tracing the graph, you never lift your pencil off. Okay, so here are just some quick examples. Well, let's take a look at another example. Now you might recall this function or this graph. It's a piecewise defined function in another video where I believe I called it the limit of a function, but this is a good graph to show continuity. So let's take a look at, say, -3. Okay, now if you take a look at -3, we do have a y value. Okay, so my first condition is satisfied. F of a is defined. Okay, so we do have a point there. Does the limit exist? Well, if you're following the graph, okay, the limit does exist because you can see coming from the left and right, I am approaching a point. Okay, so that's true. And then does the limit actually equal the y value? Yeah. So where I expect the y value to be is actually where the y value is. And so it satisfies all three conditions, and so we can say we are continuous at x equals -3. So let's take a look at another point. How about when x is 0? So if you follow along the graph, okay, is there, well, let's not do that part yet. The first step, sorry, is f of a is defined. That is true. F of a is defined. It's right there. Okay, that's f of 0. So it does have a y value. Okay, so that exists. Now, step 2 is, does the limit exist? Well, a limit exists means that when you come in from the left to 0, x equals 0, when you're coming in from the right, will you go to the same spot? And you can clearly see that this approaches, I think, was about 0.7, and this approaches -1. So my left-hand limit, again, is 0.7. My right-hand limit is -1, and because these do not equal each other, the general limit does not exist. And so we're just going to write DNE. So it does not satisfy condition 2, and so we are not continuous. Okay, again, because it violated condition 2. Okay, so let's take a look at another example. Now, based on the example we just done, you can see that we are not going to be continuous right here, because you can see that the left-hand limit approaches this point and the right-hand limit approaches down here. And so they're not going to meet anywhere, so that's going to violate condition 2. So the way you would write this is you would say discontinuous at x equals 3. And then give a reason why it's discontinuous. In this case, it would be the limit as x approaches 3 does not exist. Even though a y value does exist, it's right there, the limit does not exist. In the last two examples, limits didn't exist, which is why we were discontinuous. But let's take a look at when x equals 2. Okay, it satisfies condition 1, because there's f of 2. Okay, it exists. It's right there. The limit exists. Okay, if you're following the graph, if you're approaching from the left, it looks like we're going to a y value of 0. If you're approaching from the right, it looks like we're going to a y value of 0. So the limit exists. So we satisfy condition 1, f of 2 exists. So that's condition 1. Condition 2, the limit exists. Both the left and right-hand limits equaled the same thing, which was 0. Okay, but we know it's not defined because you can see that there clearly is a break, and it's because it does not satisfy condition 3. All right, f of 2, okay, that equals, and I want to say about 1, and the limit equals 0, and because these are not the same, okay, it's discontinuous. And so you'd write something like this, and then say, so it is discontinuous. Now there are plenty of places on this graph where it is continuous. It's continuous right here. Okay, you don't see a break, and the limit exists, and the y value exists. It exists here, so it's continuous because the limit exists, the y value exists, and they go to the same spot. Okay, over here, okay, all of these points, and you can see because I never have to lift my pencil. So places where we weren't continuous was right here. So when x equals -2, you can see when you come in from the left, it's definitely not going where you it's definitely not going to the same place. In fact, the limit coming in from the right at -2 is going down to -infinity. And what that means is that it's not going to satisfy condition 2, and you can see that f of a is defined. It actually doesn't satisfy condition 1 because there is no y value existing anywhere. So anytime you're ever asked to show that a function is continuous at a number a, show that it satisfies these three conditions. Okay, probably write them out too. Okay, that's called showing your work. And any place it's discontinuous would mean that it just has to violate one of the three. It can violate all of them, but if it violates one of them, then it's considered discontinuous.